It's good to see all of you. So, today is the conclusion of our discussion of the composition of the cosmos. So we've been talking a lot about how we know what stars are made out of and how we have some blanks in our understanding too. There's a lot of work to be done. And, you know, we're working towards next week being able to tell a story of the origins of the stars, their whole life cycle, right? It's actually kind of funny that we use this, we don't have a better way of describing the evolution of stars other than using the word life, which is, you know, in some sense a disservice, but there's something interesting to it too. There's this really awesome book called Star Maker that I highly recommend all of you read, by Olaf Stapledon. It's maybe 50 years old now, but you know, it's kind of this daydream story. It's a very poetic, very beautiful book. And the guy wakes, he has this dream. He's out watching the stars one night, and the whole book is just him having this, like, you know, vivid daydream, essentially, about the lives of stars. And, you know, what if they're actually entities that have lives, and they're going about their business, and everything that we're seeing happen is more intentional than it seems. And of course, it's complete fiction, but it raises some really interesting questions. And this week, I really hope to have some time to investigate some of the stories that the ancient peoples had for their stars. So we have only one chapter to get through in the textbook this week. So ideally, we'll make it through all of that today, and we can talk a bit more about the stories next time. Yeah. It's called Star Maker. I mean, it's a really, really awesome book. Even if you just read, like, the first chapter of it, you all should check it out for sure. Very inspirational. And you know, I don't think that it necessarily has scientific insight, but maybe it does. I don't know. It's interesting, right? Of course, stars exist on a time scale that is incomprehensible to us, at least. At the very least, the shortest-lived stars are there for millions of years. So we're never able to actually watch a star from birth to death. See, you can't avoid these words, birth and death, right? Which hobbles us a little bit because that's how humans think about things. So we're always looking at stuff in terms of life and death. And anyways, what we're going to work towards is we need to be able to tell this complete story. We desperately want to tell a story of what these glowing orbs are, how they come into being, and how they go out of existence. And the final peg in that story, before we can really glue a story together, is looking at all of the material that would go to making a star, and where does it come from. So, so today, that's what we're going to do. We're going to talk about all the little building blocks and a bit about the tools that we've developed to be able to study them. So, yeah, so this discussion is going to be rather technical, but if everything goes smoothly, we'll have some time to investigate a bit of the history of astronomy next time, because, you know, originally astronomy was tied up deeply in myth. And, you know, if you've been through the last semester, you know that I think these things are extremely valuable. And so we'll take some time to play with that. Oh, attendance. Let's start it in the back and move it down to the front so I don't forget it. All right, down one row and forward. Cool. Does anybody have any business-related questions before I launch into this? Okay, so this is one of the central players of our story today. It's a piece of chondritic dust, and we'll think about that a bit more. But like I said, we need to be able to grasp the raw material of stars before we can tell the story of how they're created. And so we'll work towards that. 99% of the material is gas. It's mostly hydrogen, a bit of helium, much like stars are. A little bit of it, though, turns out to be condensed matter, these dust particles, molecules, and those require different methods to study, so we're going to get into that. As a whole, this is all considered interstellar medium. That's the catchphrase for all of this stuff that's in between stars. And that covers pretty much everything we're going to talk about today. So in order to talk about it, we have to discuss ionization again. We have cracked open ionization previously, but I think it's one of the most confused topics in all of science, which makes it really fun to talk about. So we're going to play with what that could actually mean in terms of the structure of the atom. There's another concept that we have to deal with today, which is the concept of spin, which is a quantum property of atoms, which means that it's a purely mathematical idea that is measurable and predictable. So we're going to play with some different interpretations of that. I've had some discussions with a couple of people about the potential material interpretations of that. Where's Elijah? Over there, yeah. Elijah was very interested in this, and we talked about it. So I want to play with that idea a bit, because what we do is we actually have to use this idea of spin to observe neutral gases, right? So almost all of the light that we see has to come from gases that are in this ionized state. They have this cyclic charge state where they're able to essentially emit photons by changing energy levels. And this isn't the case for neutral atoms, which represent a great deal of the interstellar medium. And so how are we able to detect them? We have to look at spin. And that's a really complicated and confusing phenomena. And I think we're going to break it down a bit today, and that'll be fun. I got some videos for you. And then we're going to look at cosmic rays. What are cosmic rays? Well, they're not rays, unfortunately. Another one of those astronomy lingo blunders. They're actually very highly, very fast-moving atoms, essentially, ions, essentially. So we'll talk about those. They turn out to play a huge role in the excitation of a lot of this interstellar medium. They're also really important on Earth. And where do they come from? I had a really interesting conversation on the podcast with a very prominent physicist in Israel who has advanced a theory, which is somewhat unpopular, that as the sun makes its way in its orbit around the galaxy, which it does, like of course the planets orbit the sun also orbits the center of the galaxy, it's going through regions of intense density, where there's a lot of stars, and it's going through regions where there's not much. And as it does that, it's exposed to different levels of cosmic rays. And it turns out that cosmic rays can do things like nucleate clouds. And when you change the amount of cloud cover on a planet, you influence its climate very predictably. And so he has a really cool theory about that, which is fascinating. And so we'll get into that. And then all of this will lead to essentially a cycle, an idea of a cycle, just like we have, say, the water cycle or the energy cycle with respect to the radiation that's coming into the Earth and the balance. There's some static equilibrium that occurs that allows stars to be created and destroyed with regularity. And so that's what we're working towards at the end of all of this. So let's kick it off. Please feel free to stop me if you have any questions as we go through. All right. Cool. So like I said, all of this stuff is called interstellar medium. We'll just refer to it as the ISM from now on. Most of the interstellar medium is concentrated into these clouds. And we generally refer to those as nebula. They're the beautiful pictures that you see from the Hubble and from James Webb. They're usually taken in different wavelengths than visible light. And we'll get into why that is a little bit later. And there's a few different reasons for this. Mostly because, like I said, gases tend to be transparent, particularly molecular gases tend to be transparent, but also neutral gases are very difficult to detect. And it turns out that's the state in which a lot of this matter is existing. So, just like clouds here on Earth, these clouds are transient appearances. They come and go. They're going through different phases of existence. They're condensing, they're cooling, they're heating, they're interacting with the stars and their stellar wind. And so this is a dynamic process that's always on the go. Most of this stuff is gas. Most of it is hydrogen and helium, very similar to, most of it is hydrogen. And that is, in effect, reflected in the star composition themselves, which should make sense. What else do we want to say? It's kind of interesting because if you took all of this interstellar gas that's out there and you spread it out evenly, you would end up with something like 1 atom in every cubic centimeter of space, right? And remember, space is just a coordinate system for specifying location or place. So in one volume, you're only going to have 1 atom, right? Now, this isn't actually how it plays out because the universe is very clumpy, right? The material groups together. And there's some reasons for that, and we'll get into it. Historically speaking, we have primarily considered gravity to be the strongest actor in that, right? In terms of our own understanding in our own solar system, gravity has been considered as the most obvious player in the game because we see all of our planets, all of our moons, they orbit predictably through this pattern which we call gravity, which is terribly confused and misunderstood right now to some extent. Of course, we have extraordinarily powerful models of gravity, right? I mean, we're able to send spacecraft to distant moons, and we can predict the regularity of different orbits and our year and all these things, right? We have general relativity from Einstein, which refined this even further. Very, very precise descriptions of gravity. But the mechanism by which it occurs is a bit ambiguous. And we have, I believe we have at least 1 lecture, but maybe 2 devoted to gravity and general relativity. So I won't linger there too long. But needless to say, gravity is the most well-described aggregator of material. And so that's traditionally what we've kind of ascribed this clumpiness to. But there's other things happening too, right? The gas is cooling. As it cools, there's the potential for condensation. As it clumps together, it shields the inner material from interactions with, rays from stars and from, essentially from light, which would heat it or ionize it. And so you get all sorts of interesting little niches, evolutionary niches, essentially. To use a Darwinian phrase, there's a special environment that occurs due to this clumpiness, and that's going to play in heavily into what happens here. So, it's interesting because even in these clouds, the density is still extremely low, right? Actually, it's so low that when we talk about a vacuum here on Earth, like let's say we have a vacuum cleaner, right? It has really low pressure, which allows, things from the outside world, our pressurized atmosphere, to push all of the material into your vacuum sweeper, right? But the vacuums that we can achieve on Earth, even the really high-strength industrial vacuums that are needed for all sorts of manufacturing processes, they are full of stuff compared to the interstellar space, essentially, right? The vacuum out there is extraordinary. Even in these clouds, the vacuum is really strong. It could be thousands of times the vacuum that we create on Earth. I think this is actually really, really important too when we start thinking about things like vacuum tubes. This is kind of beyond the scope of this class. I don't know that we'll get into it, but when we talk about things like cathode ray guns and shooting electrons and all of this stuff, it's really important to remember that those vacuums aren't empty. They're actually full of gas, which can become ionized. And so this process of ionization, again, plays an extraordinary role in the concepts that we have of what electricity is and what an electron is. And we're going to have to deal with that to some extent today, because otherwise we're left with just talking about the motion of abstract concepts, right? And what I mean by that is, of course, that the electron is a word that we use, but it means different things in different contexts. To the chemists, the electron is essentially the outer surface of the atom. And the chemists, in some sense, are the more material-based scientists of the gang because they're really concerned with how these things ratchet together and how you make new compounds. To the physicists, the electron is a particle, which is essentially a momentary instance of some sort of measurement, right, which turns out to be like its velocity and momentum and all of this, and its effect, which is electrical in nature. And so there's some confusion because when we say an electron is transferred here, moved there, what do we mean? Because we're actually talking about a series of measurements that's getting moved around, which is actually a slight logical fallacy. It's called reification, when you take something abstract and turn it into an object that you start moving across the room. This gets very dangerous because you run the risk of thinking that these things that the physicists call particles are the same thing that the chemists call particles. And when a chemist or a material scientist says particle, they actually mean a flake of like condensed matter, some material. That's not really what the physicists mean. They just mean an instance, right? This is an abstraction. So we're going to have to play with what an electron actually is at some point here, particularly when we're talking about spin here in a moment. So hang on to that idea. So while this interstellar matter is very clumpy, there's a tremendous amount of it. Actually, if you add up the mass of all these individual gas molecules in one of these clouds, it absolutely dwarfs the size of a sun, for instance, right? It's a tremendous amount of material. So there is the possibility for gravitational interactions because the thing is just so freaking huge, right, in mass. There's so much of it. Of course, the distances are extraordinary as well, and that plays into things. All right, so here's a typical nebula. And one of the most prominent things you'll see in these nebulae is they have this nice red glow. And it turns out that that red glow comes from a particular excitation of hydrogen. And that's called the Balmer series. And that's worth remembering. But it might come, I guess it might come up in your quiz or something. But it's important to understand what these lines actually mean. And so I want to just take a moment to go over what atoms are actually doing in this case, right? So these are all of your different, this is essentially the Bohr model of the atom, which is a schematization of the atom. And what it's saying here is that the atom has different energy states, right? We call them N1, N2, N3. And essentially what happens is when the atom gets excited, when it has an interaction with some other piece of matter, another atom, through a photon, generally speaking, although it could happen by a shell-shell contact, like something electrical as well. But generally what happens is it will get excited into the next state. And as it does that, there's different photonic transactions that can occur. But let's break that down just a little bit. What does it mean that an atom is getting excited exactly, right? This is tricky. And I really think this is fun because, yeah. Yeah. Yeah, exactly. Yeah, exactly. So energy, we talked about this. Energy always, no matter what anybody tells you, energy always comes down to some material in motion. Always. This is kind of a foregone conclusion that people don't really talk about a lot. And that's why I think it's really important to think about what the atom is doing. So what does it mean? And like Theodore says, it's moving faster, right, at each one of these. So with a simple atom like hydrogen, it only has one electron in its orbit. It's a very simple hydrogen. And that outer surface of the atom is pulsating like this. Well, when it gets kicked into a higher energy state, it pulsates a little bit differently, right? More frenetically. And so, if you kick it into really high energy, right? If it gets a lot of juice, then it's going to start making interesting shapes that don't have that spherical size. They go into different orbitals, right? That we'll call them p or d orbitals. And actually, some of the really complex molecules, like the metals, for instance, they have all sorts of orbitals, right? They take on all these conformations. So what's important to remember here is that the way that it's getting kicked into these interactions is through collisions with other atoms and through light itself. When light is able to, from one atom to another, to excite that atom into a new phase of motion, okay? So each one of these transitions gives off a particular flavor of light, right? A particular frequency. And so that's what people are measuring, is they're measuring these actual emission and absorption spectra. When an atom receives some sort of light impulse from another atom, it gets excited, and when it releases light, it de-excites, right? It relaxes. And so as it relaxes, you get an emission that has a particular wavelength, depending on the atom, in this case hydrogen. And when it's excited, it has a particular absorption. And we talked about how you can see absorption lines as these black lines, right? You have a big continuous spectrum from a star, let's say, a big rainbow, and then you'll get these black little lines over it, right? Those are absorptions. And then the emissions are the same lines, but they're going to be bright, okay? And you don't need anything in the background for those, right? Okay. So these are some of the main transition series that people look at. In particular, this red one comes down to that Balmer series, right? It gives us this nice characteristic red glow. All right. What else do I want to say about that? So these Balmer lines are particularly apparent when gas is in the vicinity of a star that's around 10,000 Kelvin. And when I say it's around that, I mean like its upper chromosphere is in that, the excited gas region above the pseudo-surface of the sun, whichever sun you're talking about, star, is going to be in that 10,000 range. So that happens to be nicely fit into our own sun, which is, as you know, a very middle-of-the-road star. And so this is pretty common for gases that are in the vicinity of stars. And that works well. This is actually called a hydrogen-2 transition. This isn't too important for you to remember, but it's a very common sight to be seen in these nebula. Unfortunately, it doesn't work very well if you get away from a star that's of that particular temperature, and so we have to have some different methods, which I'll talk about. Now, ionization itself is what we're talking about here. So when that atom is doing that jumping, right? You often call it quantum jumping. Another way that it's often described, particularly in chemistry, is that this electron is being removed from the atom. And what does that actually mean? Well, is the atom losing its surface? Well, there's not really any reason to believe that it actually is losing its surface. It's just that in an ionized gas, in a plasma, right, like these lamps that are above our heads right now, you have a situation where the surfaces of the atoms, the electrons, are distributed amongst the atoms, right? They're sort of blended together in this really interesting way. And I think that's the more appropriate way to think about ionization, right? You have these atoms, their shells are expanded and stretched in such a way that they can electrically engage with one another, but they're not localized in the same way. And this is also how you can think about metals to some extent too, which is really interesting. Metals also can be treated as if they have this quantum gas of electrons, right? This is an abstraction, though. It's maybe a bit confusing. I think the more appropriate way, again, to look at metals would be that their shells are kind of, at least the shells that are important in conduction, are in some sense blended together, right? They're sharing their electron surfaces in a way that allows them to conduct motion from one atom to the next very rapidly. Okay, so, you know, the physicists will often describe the electron as being removed during ionization. This is kind of like a standard textbook picture of this, but it's a schematic idea, right? Do you know what I mean by schematic? I mean like a wiring diagram, right? It tells you how things are happening. It doesn't necessarily get at the underlying physical mechanism of what's going on, though. And so, you know, it's bewildered me throughout my own career that people aren't more concerned with the actual happenings. But in some sense, it makes sense. In some sense, it makes sense. It makes sense because for technological applications, you don't really need more than a schematic, right? If I'm going to go and fix my microwave, like I destroyed my microwave like a year ago on accident. I was like sterilizing a sponge in it that I was cleaning my kitchen with, and it caught on fire, and like it was horrible, and it stopped working, and I was renting this apartment, so I had to fix it. And anyways, I took it apart, but I needed the wiring diagram to do it. But I didn't have to know like what the atoms were doing inside of the microwave in order to fix it, right? I just needed to know what parts go where and what their voltages are and make sure I get the right thermocoupler and the resistance is right and all these things, right? So in general, in terms of developing complex and advanced technology, all we need is that schematic representation. And that is why these kind of representations are so popular, because they're functional. They work really well in terms of incrementally developing new technology. And we live in an engineering-dominant scientific culture, right? You know, if you're going to go into science, and I hope some of you will find very quickly that even if you're just studying something because you think it's cool, like how stars work, you need to ask for money to do that in a way that's technologically relevant, right? You're going to have to say, okay, well, these sensors we're going to build for this satellite could be useful for blank. Communications projects, defense projects. It's always, in our culture right now, all of our scientific knowledge is instrumentalized. And, you know, I'm not totally trying to pass a value judgment on this. I think that there is a lot of good that comes out of that. But there's a lot of blind spots that result from it as well. And one thing I spend a lot of time thinking about is, you know, 1,000 years from now, assuming our species is still around, is this how we'll still continue to do things? Or will we have set up some sort of protected space for scientists to do work in a way that isn't necessarily motivated, right? Because a lot of the fundamental science that was done, particularly during the Enlightenment period, but we can go all the way back to the Greeks, these guys weren't really trying to build stuff, right? You know, it's really evident in the Enlightenment thinkers, because you think, who are these guys? Who is Huygens, you know, with his wave theories of light, and Young and Hooke? Like, these people were all basically wealthy aristocrats or professionals, doctors, lawyers, something like that, right? They weren't really motivated by making a career out of science. They were just curious. It was something like a hobby. They didn't have Xboxes and stuff, so they thought it was really fun to figure out how nature worked. And, you know, I don't think it was a coincidence that they made great leaps because of this. They were just purely motivated by their curiosity. This is something that's very difficult to achieve in the modern landscape. Yeah?
You say that the Enlightenment model of science, that sort of way where we raise people and people trying to figure stuff out based on career incentives, was that a better way of doing things? Or a better way of doing science?
I mean, this is tricky because like better implies like a value judgment, right? Right. So I do think, okay, so I can say a couple of things objectively though. Scientific innovation has completely stagnated actually. So there was a Nature paper that just came out that looked at, the metric that they used was kind of interesting. Let me just state the conclusion was that scientific innovation has completely flatlined. The way they looked at that was they said, who's coming out with papers that they don't cite other people on? So they're not building on something necessarily incrementally. They're coming up with brand new ideas, and then that idea is cited in future literature. So they analyzed it, and they basically saw this like complete, you know, drop-off across the last 100 years or so. Of course, scientific publishing in the way that we think about it has only been around for about 100 years. So, and that's a concern. objectively. People are worried about that. Why are we not making huge breakthroughs anymore? And I do think, like, to answer your question, that that wasn't an issue before science was technologically motivated. Particularly that happened during the Industrial Revolution when people started to make engines, right? They were like, oh man, we can stop paying these people, or we can stop dealing with slaves if we just make machines to do the work for us. And so that really brought on the career scientists for the first time. The revolution of medicine, also industrial medicine, is where most careers are in science. Almost everybody that I know from working in labs and coming up through grad school is working in an industrial capacity now. There's very few people that are professors, and particularly in industrial medicine, right? That's a huge cash cow. I mean, that's a huge career building situation. You know, and there's merits to that, of course, but it doesn't seem like it's necessarily led to groundbreaking new paradigms of how things work in nature. And there's not really a protected space for that. So, you know, I'd love to hear your guys' ideas. It's just something that my wife and I think about a lot. We talk about, we ask almost every scientist we encounter, because most scientists you encounter, they're aware of this issue. They're a bit fed up with it, but they don't know what to do about it at the same time. And so I think it's really important that we dream up and we use our imagination to imagine how these processes could be done in a more effective way in the future. I think it's always really important to think about what humans are going to be like in 1,000 years. Hopefully they have all the best characteristics of us and they get rid of the worst characteristics of us. That's sort of the model that's the only thing I can imagine which is worth working towards, really. So we'll see about that. I guess we won't see. We won't live, but, you know. All right, questions about all of this? Anything? Cool. All right, so ionization, this is important. This is essentially how new light is being formed. This is how absorption is happening. This is the bedrock of all of our spectroscopic analysis and essentially how we're able to view this material. Much of it which appears quite transparent or even blocks out light, which we'll see in a minute. Okay. So, you know, these hot stars, they're able to, some of the hot stars in the 10,000 K region that we were talking about are able to heat the gas in such a way that we get this nice Balmer series. There's also ultraviolet radiation, which is not necessarily heat-based, but it's able to ionize hydrogens too. And this is interesting because you'll get recombination, right? You get these ions which get excited, they relax, and you can see other lines as a result of that. Neutral hydrogen itself can absorb ultraviolet radiation, which is quite interesting. So it doesn't have to be charged in the same sense that we generally think of plasmas and how we've gone through previously. And so there's this cycle of absorption and emission that continues and continues. Let's see, what do I want to say? Ultraviolet radiation. Okay, so a good example of this actually is the fluorescence process that's like happening in these lamps right now. Because actually what's going on is when we pass the when we apply a voltage to the gas inside of these lamps, it's actually I believe it's a mercury ion, a mercury gas that's in these things. But the color of that isn't appropriate. That ultraviolet radiation that's emitted isn't something that is visible to our eyes. So what they're doing is they are actually impinging that that ultraviolet radiation from the gas in these lamps is actually impinging on this particular phosphorescent surface, another atom, which is coated in the edges of the lamp. And that is getting excited. And when it drops down, it gives off something we call fluorescence, which is a visible light that we can see. So there's a series of these transfers of photons, right? Where something is getting excited, it's too excited, we can't actually see that light, but we make it useful. And the same process is happening in interstellar space. So there's a lot of conversion, and ultraviolet light can play a role in converting to new levels of light that we can actually observe being emitted from these different gases, which is pretty cool. All right. So, like I said, a lot of this gas is visible through these immediate surroundings. They're close to something warm that is ionizing them in this nice way. The neutral hydrogen is a bit trickier. Neutral hydrogens are at the temperatures, these are very cold. These interstellar regions are cold. They're not necessarily near a star. And so typically, those can't really absorb or emit anything in the visible spectrum. So they go through this process we're talking about. Sometimes other elements that are out there in the interstellar medium can absorb at those frequencies. We're talking about calcium for the most part, sodium. There's individual elements that are bigger than hydrogen, and we have to actually think about where those come from. We talked a bit about it before, but most of the heavy stuff that's out there is coming from something that has passed, a star that has passed, and it's gone through some sort of violent eruption. And there's different ways that that can happen, which we'll get into better next week. But this is the general picture of what we're talking about. So, you have a very nice star with its absorption lines. The broadening of its own atmosphere is going to be visible because there's a lot of pressure at the surface of the star. However, when it comes through some sort of interstellar cloud or dust, well, dust is different, but let's stick with clouds of gas for right now. You're going to have new excitation bands that appear, and they're going to be quite thin, actually. And so these can be separated out from the actual star because they don't have the same width to them. I thought it would also be cool to just show you guys what hydrogen looks like when you split it up with a prism. And this is it. So this is a hydrogen lamp, and what's pretty cool. So this is being excited, so we're seeing the emission bands of hydrogen. But you can imagine that the absorption bands are the exact same as the emissions. They're just black, right? They're going to be bands. And actually, hydrogen splits up into some very beautiful different colors, in particular this red one, which we've been talking about at length, this Balmer series. Now, so you can look at the way that perhaps the neutral gas is interacting with ultraviolet, but that's not always entirely useful because ultraviolet radiation is not going to penetrate into a dense cloud very well, right? This is apparent on Earth because, you go outside and, there is some penetration, but it's not nearly as bad as on a sunny day. You're probably not going to get a terrible sunburn when it's super cloudy outside, right? This makes sense. So condensed matter, in our case, it's water vapor, but it turns out actually there's a lot of water vapor in these clouds as well, a really significant amount of it. And we haven't really talked too much about molecules yet, but molecules are essentially just complicated multiple atoms kind of glued together or sharing some part of their surface. It's stuck. So this UV doesn't always penetrate, so we have to do something else to look at it. And the way that we analyze it is through this, generally through radio telescopes. And the reason for that is that there is a particular kind of transition which is not exactly ionization, which is called the spin flip process. And your textbook mentions this a bit, and it's worth going over because this was a huge discovery, which is, one of those triumphs of mathematical physics because the presence of this particular spin flip line, this light that was emitted through the spin flip, totally different process than ionization, and we'll get into it, was predicted before it was observed. And as soon as it was observed, once they were able to create radio telescopes, it allowed us to see all of this neutral hydrogen for the first time, which was really huge because we thought it had to be there, but we couldn't see it. Now, spin flip is a bit of a confusing concept, and I do want to take some time to think about it because it's very different in this idea of light being emitted as a result of the breathing motion of these atoms, right? And the way that your textbook lays it out is something like this, which again, very schematic, and I don't think that it's incorrect. This is probably a good way to start thinking about it. So the different regions of the atom, let's say the nucleus, the proton, and the shell, the electron, they have a particular magnetic moment to them. Another way of thinking about this is they just have a particular surface motion, which is qualified by this concept of spin. It tells us about the momentum and the direction of the motion, right? Now, this turns out to be integral in quantum mechanics because it allows us to specify what we're looking at when we view a particular interaction, say in a collider or something like that. Well, one of the properties is that generally the proton, the center of the atom, is spinning with an inverted symmetry to the outer surface, the electron, the shell. And generally, this is how hydrogens exist and all other molecules. But there is this moment that happens where the outer surface inverts its spin. It flips, switches, and the shell is moving in the same direction as the interior, which is actually energetically unfavorable. It requires some sort of kick for this to happen. And when it does happen, it actually relaxes and gives off a very, very weak form of light, which is actually occurring in the at the far end of the electromagnetic spectrum in the radio wavelength. So the 21 centimeter line refers to a wavelength where the wave is actually 21 centimeters long, which is pretty big for a light ray, right? For a wavelength of light. Okay, so, I spent a lot of time thinking about this in general. What is actually going on with the atom in this case? And, spin is a strange quality because it would be tempting to think about spin as just, okay, it's just rotating one way or another. But there's more to it than that. The surface of the atom is actually precessing, right? The angular momentum, if we measure it in these colliders and in these deflection experiments, we see that not only is the electron spinning, as it's called, but there's also a strange symmetry that occurs. And this is how spin, the particular spin, which is called spin 1/2 for an electron, is illustrated on Wikipedia. I think this is what most people draw it as. The strange thing about spin 1/2 is that the surface has to rotate twice to get back to its starting point, which is very strange. And most quantum physicists will say, okay, well, this is just an instance of the fact that the microscopic world doesn't make sense, right? Well, I think that's a bit silly. I think there has to be an explanation for it. I spent a lot of time thinking about this. And this is of course what you'll find on Wikipedia. I think this is an interesting idea. Maybe the electron looks something like that. But I think that there's a more integrative way of looking at it because we know that the 1s shell, the very simple hydrogen shell, is approximately a sphere, right? We have different ways of looking at that. We can actually use really cool microscopes to touch atoms, essentially, where we can actually get topography. And fair enough, they look essentially like spheres. Yeah.
So is this how the whole atom spins, or is this just the electron cloud?
Yeah, just the electron. However, I'm going to show you in a minute my own particular representation of this, which I think looks a lot more like an atom. And so I think it's important because this plays into the idea of what spin flip is. Why would this completely invert suddenly when it gets kicked the wrong way, right? That's the problem with getting stuck in these schematic representations of the atom and so forth. Is you really are hard pressed to come up with mechanistic explanations for what's actually happening to that material actor. Most people don't care, but I think it's going to be a huge topic of inquiry in the next 100 years, maybe next 10 years, hopefully if I'm lucky, the next 5 years. So another way of representing spin with a symmetry that's conducive to this particular double rotation to return to its original point is kind of how I've illustrated it here. Let me see, I might have to push play on this movie if it doesn't play. The surface of the atom could be thought of as involuting, such that as it makes two turns, the equator has moved around the outer surface through the inside and back to the beginning once. I think this is, in some sense, at least a better visualization of it because it actually has a surface like a shell that's approximately spherical. And so what you have is a motion on the surface, which is also commensurate with the angular momentum vectors, right? It is precessing in a way if you add up all of the angular momentum of the surface. But as it turns, it takes two rotations to get back to its starting point. And I've just put a yellow or a pink line on this. I'll say it one more time for you so that you can see the equator as it changes. So I'm not saying this is what's happening. I'm saying this is a good way of thinking about it that's congruent with the mathematics. Maybe it is what's happening. I don't actually know, but that's going to take a lot more inquiry for us to figure that out. But the cool thing about this is that it allows us to come up with some idea of what we could mean when we say spin flip. Because it turns out that in the macroscopic world, there are places where we actually see spin flip happening. And in particular, there was one discovery that was made by the Russians, which absolutely freaked them out. And so I'm going to play you a video next of what the Russians saw when they were in space. This was back in the early days of the space race. They actually, when they discovered this, they kept it as a top state secret for like a decade because they were so worried about the implications of what it meant, which is quite fascinating. And this is what the Russians saw. They were actually unscrewing a wing nut at the space station, and it flew off of the screwing assembly, and it started to do something kind of weird. As it spun, playback's not great. As it spun, it inverted every few turns, right? So the wing nut was spinning, came off with all this momentum. And then every once in a while, the spin would invert on the thing, right? Which is freaking crazy looking. Okay, so why were the Russians freaked out about this? Well, first thing they did was they started playing with other objects, right? And they took a bunch of clay and wound it onto this wing nut. And they said, would this happen with a sphere also if it had a slightly offset center of mass? And sure enough, the sphere was doing the same thing. It would spin one way, and then it would spin the other way. And all the Russian scientists got together and they were like, oh my God, this could happen to the Earth. Right? So they were like, we can't tell people about this. Right? People don't want to hear that the Earth might just flip over every once in a while. And there's, of course, we've talked about it in the last bunch, but people are very allergic to these catastrophic descriptions of history, right? We always want to think that things on Earth kind of proceed very smoothly and steadily. Everything's going to be cool tomorrow because it was cool yesterday. And so they're very, very concerned about this. And so I'm not sure what the real conclusion of that is with regard to the Earth. Certainly, there's no definitive evidence that this is happening. And a bunch of mathematicians got together and they analyzed this concept to death. And they concluded that essentially because the Earth is an oblate spheroid, in other words, it's stretched a bit at the equator, that that moment of inertia at the equator is maximized, and therefore it adds stability to the system, right? In other words, if the wing nut didn't have this little stick coming off of it, if it wasn't off center, if it didn't have an extra pull in one direction, that those little instabilities wouldn't build up and pull it over to the side, right? Now, why am I telling all you guys this? I think that, I would hypothesize that something very similar is happening with the electron during the spin flip process as well, right? A little bit of an instability, in other words, a very tiny kick from another atom crashing into it, maybe what we would call a cosmic ray, which is the high energy atom that's flying through space. Something could disturb it so that its spin rotation axis was slightly put offside, which would lead to an inversion of the shell like that. Just a hypothesis. But I think it's a good way, at least, even if it's not actually what's happening, it might be, but even if it's not, it's a good way of visualizing the spin flip that at least has some sort of real material significance for what could possibly be happening. Questions? All right. Cool. So there it was. They had this observable characteristic that we could view neutral hydrogen, right? Non-ionized hydrogen. It was undergoing some process that would have a characteristic signature that we could see. They call this the 21 centimeter line. I just don't have enough power in my computer to make things work sometimes. Come on. All right. Okay, so this equipment didn't arrive until the 50s. We didn't have radio telescopes. So, you know, of course, again, this is one of those really squidgy regions where we got this amazing radio technology. Where did it come from? Well, people were fighting enormous wars in the beginning of the 20th century, right? So radio technology and radar and all of these inventions were the product of wanting to absolutely obliterate other peoples off the face of the earth. So, you know, great technological progress can come out of these terrible conflagrations and chaos and madness and death and destruction. So this is where you run into these like value judgments, right? Where it's like, you know, what's the cost of progress exactly, right? There's no easy answer there. And there's no indication that the spirit of war is something that we're even capable of eradicating from our own selves, let alone from our society as a whole. So I don't know that that's going to disappear anytime soon. I mean, the good news is war has gotten a lot less ugly in some sense. There's certainly not these massive fronts happening anymore like they used to. War is actually killing way less people than it ever did in the past throughout all of human history. But the spirit remains, right? People still get in fights all the time. People are very quick to jump to aggression, even in their own language, right? When they get uncomfortable, when they get to a point where they can't agree anymore. So I don't know. We'll see what happens. But hopefully, like I said, in 1,000 years, we'll have figured out how to preserve the best parts of ourselves. All right. So, you know, this is interesting. This 21 centimeter line is interesting because it's a very rare event that a neutral hydrogen, remember, they're so spread out from one another that it's extremely rare that one of these would even get kicked by another atom. You know, it's estimated that an atom sits around, a neutral hydrogen can sit around for, on average, for 10 million years before it gets punched by another atom randomly and is excited into the spin flip situation. So they're really, really stable, generally speaking. It just so happens that there's enough of these atoms that waiting for 10 million years on average is totally fine because you can always do a few of them here and there, which is kind of, the scale of these processes is just beyond, really beyond our comprehension. I mean, it's hard to imagine 100 years, let alone 10 million years. Before we were able to go out into space and see X-rays for the first time, most people assume that all this gas is very cold. And it's interesting because it's, you know, thank God we can't see X-rays on Earth, right? If we could see X-rays coming from space on Earth, it would be really bad news for us because X-rays turn out to be quite resonant. The wavelength of an X-ray is quite resonant with your own DNA, and it will shake your DNA apart, and that's not good for your body, right? For obvious reasons. So our atmosphere is this wonderful blanket which actually shields most radiation that's potentially impinging on us from space, but very conveniently allows visible light through, right? This is, you know, it seems like something of a miracle, but obviously we evolved in these circumstances for that nice little window, right? So I don't think it's a coincidence that we see visible wavelengths and that our atmosphere only transmits visible wavelengths. A little bit in the radio, a few radio frequencies also make it through. But for the most part, our atmosphere is completely opaque to most radiation. This is a wonderful thing. So people didn't start seeing X-ray emissions until they actually put satellites outside of our atmosphere and we were able to start looking around. And when they did that, they noticed that there was actually that the cosmos were bathed in ultraviolet radiation all over the place. And in particular, they were finally able to explain why it was that they saw oxygen atoms that were in these really highly ionized forms, like 5 degrees of ionization, if you think about those energy scales. These oxygen atoms were undergoing transitions that didn't make sense because it didn't make sense that the radiation was there this high energy ultraviolet radiation was even possible. And so it's a bit surprising when people started finding essentially these really hot gases, right? When I say the oxygen's in a high degree of ionization, it's extremely hot, right? Those surfaces are moving very, very fast. That's one way of thinking about it. Temperature and speed are essentially the same idea when you get down on the atomic and molecular level. Okay, so there's these bubbles of very hot X-ray emitting gas that was out there. Oh, sorry, I said UV before. I'm sorry, I'm talking about X-rays. So that gas has to be something equivalent of millions of degrees, right? And this was pretty difficult to explain how there was gas that was heated to this degree. It wasn't near stars necessarily, and of course these lone regions of gas, these bubbles, are supposed to be really cold, right? There's not much going on out there to heat them up. So people had to start thinking about what processes could do that. And the only thing they could think of was supernova. That when a star explodes, as they sometimes are thought to do at the end of their lives, and we've observed some of these events actually, that there's a shock wave produced, right? Much like an atom bomb or something when it goes off, or say a really loud explosion, right? There's a ton of energy in that shock wave. You know, most people, like, you watch like Hollywood movies, you see these explosions, these fireballs, and like the bad guys are getting blown up and everything. You think like, okay, the bad guy got cooked by this bomb or whatever. But it's actually the shock wave that does the damage, right? That's where all the energy it is. And like, not to like completely get disgusting and graphic here with you, but like, usually when people get hit by bombs, that shock wave compressing their internal organs is what does all the damage, right? This is a horrible thought, but it's important for you to understand how much power is available in the shock wave. Now, if you take a bomb, let's say just a hand grenade or something, and that's capable of absolutely decimating somebody's internal organs, think about a star exploding, okay? This is an unbelievable amount of power, particularly since some of these stars are absolutely gargantuan compared to our own. So we're talking about tremendous energy that heats the gas to these tens of millions of degrees. You know, and there's enough of these that these supernovae are exploding every few, let's see, every few million years. And so the thought is that periodically one of these bubbles of hydrogen is close enough, or, you know, not just hydrogen, but one of these bubbles of gas, particularly as evidenced by the oxygen, which is somewhat outnumbered quite a bit by the hydrogen, but it will be excited to the extent that it can actually emit these highly ionized bands that we can see. So there's one line of evidence for what's going on at the end of a star's life, and we'll get more into that next time, or not next time, but next week. This got people thinking about molecules, right? Not just atoms, but molecules, the presence of molecules out there. And they went looking for them, and they found quite a few, actually. So it turns out there's actually really quite complex molecules that occur in these bubbles. And, you know, some of the most common ones are a bit simple, like cyanide, or very simple hydrocarbons, you know, a carbon with a hydrogen tacked onto it. But some of them can get quite complex, like different organic compounds, like formaldehyde, things like that, that are actually these big chains. And of course, this leads to all sorts of questions of where those come from. And this was a bit surprising to people because the thought was that, okay, space is full of all of this really hazardous radiation. Things that are big should be completely ripped apart, but this isn't what we see happening. And the reason for that is because they're essentially protected down inside. And down inside of some of these clouds, there's dust. Now, dust is a really wonderful shelter if you're a molecule, because it has all sorts of nooks and crannies that you can hide out in. And that seems to be the process that allows for this advanced chemistry to take place, where we get the production of these molecules. Because, you know, a big part of chemistry is that you can actually have an atom hang out long enough next to another one for it to combine, right? If they're flying around at tremendous speeds, you're not going to have much recombination. So dust plays a big role. So that's so dust is essentially our final player in this story. Now the interesting thing about dust is that it essentially makes a big black space in the sky. So if you look up at the Milky Way, say, stick with me here. If you look up in the Milky Way, you're going to see these. Somebody has completely fallen asleep. All right, so if you look up in the Milky Way, what you see is these patchy regions, right? You see actually what look like holes in the stars. There's big blank regions. And this turns out to be mostly that dust. So what do I want to say about this that's interesting? You know, another thing that's thought to occur here, which is quite interesting, is that most of the molecules that are out there in these clouds are a good portion of them are thought to be comprised of molecular hydrogen. That's essentially two hydrogens stuck together. The problem is when you have something like hydrogen, it doesn't actually absorb or emit light. It's a perfectly nonpolar molecule that has no real electrical properties to it. And so how do you know when you have molecular hydrogen? And what we do, for better or for worse, is we say that the same reactions that produce carbon monoxide, which is a very polar molecule that has a really nice spectroscopy picture to it. It plays well with light. It occurs in proportion to hydrogen gas. And so whenever we see carbon monoxide, we can assume that there's probably a few hydrogen molecules that are there as well. This actually turns out to be one of the most heavily debated topics in all of molecular astronomy right now, because the reliability of that correlation is very up for grabs. And there's all sorts of observational evidence that the value that we have for this carbon monoxide to hydrogen ratio isn't really appropriately applied everywhere. It might be correct in one region where we can see these reactions occurring that would produce both, but there's not really good reason to believe it's happening everywhere. So we don't really know how much. We don't really know how much of these clouds actually contain molecular hydrogen. The best guess we have is by looking at carbon monoxide. So we get some really cool looking molecules too. This is what we would call a fullerene ball, graphene, which is a very complex form of carbon, which actually makes a great blackbody absorber. All of the original blackbody experiments were done with carbon. There's also, like I said, a great deal of water out there, which is really interesting because the presence of water at the time of the formation of stars and the star systems has really changed the way we think about how we got all of our water here on Earth. When I was in college, a million years ago, the story was that the Earth was slammed with comets, and that's how we got our oceans. And I remember sitting there being like, man, that's a lot of comets. Like, this is hard to imagine. I didn't really buy it, even though I knew nothing about anything. But it turns out that people have moved away from that because they've discovered that there's a tremendous amount of water complexed within our own crust and deep in the mantle as well. There's a particular form of magnesium which binds waters to it, not in a liquid form per se, but holds on to tens of water molecules per ion of metal. And there's estimates that there's as much as 6 times the water in our oceans below our feet bound up in the minerals themselves, right? So what I'm trying to get at is that there's plenty of water out there to make water worlds like ours or like Neptune, right? If you took last semester, we understand that these ice giants are in large proportion comprised of water, as well as some other things, ammonia and different other things. But they exist as ices because it's very cold. So there's a lot of water in these clouds, in addition to carbon dioxide, oxygen, basically all the stuff that you need to make a planet, which is really cool. And a sun. Some of the biggest molecules have something like 60 or 70 different carbons in them. That's this one. I don't think it has 60 or 70 in this picture, but they can get quite complex. And we'll talk about how those are produced when we talk about the death of stars, which is quite fascinating. All right. Here's a picture, by the way, of one of these dust clouds, right? And this absolutely perplexed people when they first started seeing these. They really thought of them as tunnels, right? There was just big chasms that opened up, and they went into the deep distance. There was just places where there were no stars, and it took a lot of hypothesizing and testing before people were able to actually conclude that, no, we're just screening out the light. It's just dust. You know, we can see that not just from the blocking of light, but also dust, like I said, a lot of it is very sooty, right? Like it's very carbonaceous. And what we know about black bodies is that they absorb radiation really well. And in this case, they absorb heat energy really well, and they emit as well, right? So anything that absorbs a particular wavelength also emits in that wavelength. So these things give off infrared radiation really, really nicely. And so I have a picture of that in just a second. The other thing that they do is they can reflect and diffuse the light from nearby stars. So they can make halos, right? Like little dust clouds. You've probably seen this in your own life. So, you know, here's a picture. On the left, you see these stars in the visible range. And then on the right, you can see what it looks like in infrared. And you can see these enormous glowing streams of dust and so forth, which is quite interesting. This actually turns out to be the Horsehead Nebula in Orion. So they glow very brightly in the infrared, and that's one of the key ways that we know that there's stuff there and they're not just these giant gaping holes. And then there's also this presence here, which is you can essentially see these little halos. If you have dust in the vicinity of a star system, you can get this phenomenon, this reflection. We call these reflection nebulae, actually. And in this case, you know, there's cases where the stars, where the emissions of the dust and gas, let's say the gas is actually brighter than the stars themselves. And this really has to do with the temperature of the stars that they're in proximity to. If it's a very cool star, that can occur where the gas is actually brighter than the star. You can also imagine a situation where the star completely outshines the gas, and it's very difficult to separate the two from one another. Cool. So there's one more process that we can use to look at the presence of these dust clouds, and this has to do with the scattering of light, particularly the reddening of light, which is interesting. So this process you can actually see in the morning or at sunset, right? The sky becomes very red at night. And a lot of this work was done by James Jeans, actually, who we talked about, who kind of lost the battle with Eddington for the composition of the sun. Jeans and Rowley were actually succeeding in producing an explanation for why the sky is blue, which is a really interesting question, and why the sunset is red. And it has to do with the way that light is scattered or relayed through the atmosphere. So when the sun is at a low angle, say it's going down at sunset, it actually has to traverse a great volume of atmosphere, right? If it's directly over your head, it's going through a little thin slice. If it's coming from a low angle on the horizon, it's going through all of that atmosphere, right? And so in the process of doing that, a lot of the light is getting deflected or absorbed. It turns out that in the case of, we call this process as a whole scattering. But essentially what's happening is that the lower frequencies are more easily relayed directly forward, and the higher energy ones are getting scattered off in different directions, right? They're getting diffused. And so as a result of that, this process as a whole in astronomy is called interstellar extinction, not to be confused with the dinosaurs or something, but what we're saying is that some of the wavelengths are getting extinguished. And so as a result of that, here's a little schematic from your textbook that shows you what's happening. Come on. Yeah, so as it goes through these clouds, you're seeing essentially that the red ones are those that make it forward. And there's a very particular quality to which this occurs. It's distinct from, say, something like black body radiation as a whole, or the cosmic black body radiation, or something like that. So we can separate out this process. All right. Water is tricky. To some extent, water is a refractive process. But yeah, I would say that it is essentially the relay of light. In liquids, it's a bit interesting because the molecules are in contact with one another, right? Which is a bit different than light in a vacuum, where you're looking at the extended portions of the atom that are conducting the light. But yeah, you do see wavelength separation in liquids and in prisms and stuff like that as well. And it is essentially a very similar process, yeah. I think that's a reasonable way to think about it. Okay. So, what do I want to say? We've talked about the dust. You know, the dust particles are essentially molecules. They're often these, the volatile liquids are now frozen into ice-like particles, so they actually look a lot like comets, but very tiny. Not a ton to say about those. I guess you can just read more about dust if you're interested in it. There's a whole chapter in your book. I do want to maybe talk at the end here about cosmic rays a little bit, because I think they're quite fascinating. And I also want to plug this conversation that I had that I think you might enjoy. So cosmic rays were actually discovered in 1911 by this Austrian physicist, Victor Hess, who was actually playing with some instruments on balloons and was realizing that there was interactions in the upper atmosphere that weren't as evident down below. And he called these cosmic rays because they must be emanating from space. Of course, again, like I mentioned earlier in this talk, that the term ray is a bit misleading. It was a while before people were, I don't know that they've really separated it out so far, but we have things called like cathode ray guns, which are essentially vacuum tubes with electrical phenomena going on inside of them. The idea that electricity was conveyed in rays is a long-standing concept. And it's actually not quite a ray. It bends under the influence of magnetic activity. And that's actually what makes cosmic rays so tricky to put your finger on, because we want to be able to say where they came from, but it's not that easy. With light always travels in a rectilinear fashion, right? It goes in a straight line. Particles, electrically active particles, atoms, electrically active, they get pushed around by magnetic fields. And so it was very difficult, and still remains very difficult, to pinpoint the source of cosmic rays, because they're actually getting rocketed around, and oftentimes they'll spend millions of years traveling back and forth inside of the shock wave of a supernova before they're actually able to exit, before these particles are actually able to make their way out and find their way to us. And so that's made understanding the source of cosmic rays very challenging, and it still remains a big topic of inquiry. So I'll just leave you guys with this. Nir Shaviv was a really fascinating dude. I highly recommend. He got some short videos on YouTube. We did a long-form podcast with him, and he's really considering the location of the production of cosmic rays with respect to Earth's climate as it moves its way through the Milky Way. And he's found some interesting correlations with how that times to a lot of the different natural changes that have happened on Earth. So last thing I want to say to you guys is we're going to do another hour before class on Thursday. It's been really fun for the few, it's been different groups of people who have shown up every week. So bring a cup and we will chop it up about all things astrophysical or whatever. I'll see you guys. Have a good week.